Hello, thank you everyone for joining today. My name is Nicholas Lopez. I'm currently a junior in electrical engineering at the University of Texas at El Paso. My project that we're working on today is the effect of strain on vibrations in cubic cesium-lead iodide perovskite. This project was done in collaboration with the University of California, Merced. I got to work with Kuntal Talit, a grad student in the physics department, as well as Professor Struber, also in the physics department. So a little bit of background about perovskites. They were first discovered by Perovsky in 1839, with the first one being calcium titanium oxide, and they typically have the structure AbX3 with two cations joined by one anion, as shown in the top left figure. Also, some applications are that they can be used to increase the efficiency in solar cells, and they're more cost efficient as opposed to materials like silicon. Why exactly cesium-lead iodide? We chose it because it has a more stable structure, and we kind of wanted to own in on reducing the degradation due to overexposure to sunlight and moisture. You can kind of think of strain as a coil or a spring where you can stretch or compress it however you need to, and it can be in different directions. However, for this project, we applied uniaxial strain to the perovskite structure, and we wanted to look at the IR infrared spectroscopy. Look at the energy wave cutoff as shown in the figure on the top left. And we chose the convergence of 80 because we wanted something to be less than 0.01 of a difference when you look at the convergence. So if you really kind of zoomed in right there, we saw that 80 was the best value where it started to converge. The same thing, we looked at the K-grid and saw that 6 by 6 by 6 was the optimal value, was the optimal structure. And as you can see below, these are the lattice parameters that we got out of the optimized structure in the different functionals such as LDA, PBE, and PBE sol. And you can see that the lattice parameters and bond angles are in good agreement with other works in literature. Once we had the optimized structure, we took a look at the band structure. And originally we had 22 cone sham states and added 10 extra bands to do calculations through LDA so we can look for Raman activity. And band gaps are important because we want those kind of tell us the conductivity of the material. And as you can see in the figure at the center, we have the different functionals used to compare key points R and M. And also in the other figure, you can see that our band gaps are in pretty good agreement with other works in literature. And also in the band structure figure at the bottom left corner, you can see that the band gap matches up pretty well with the density of states graph. Once we had the optimized structure, we took a look at the band structure, and we originally had 22 cone sham states and added 10 extra bands, making it 32 bands in our calculations, and we did it with the LDA functional to look for Raman activity. So as you can see in the figure at the center, we compared K points R and M with the different functional, and as you can see on the other figure that the band gaps are in pretty well agreement with other works in literature. And band gaps are important because they tell us the conductivity of the material. Also, you can see on the graph that the density of states graph matches pretty well with the band structure. We did a couple of phonon calculations to observe if there was any Raman activity, but there wasn't because the structure was highly symmetric, and we ended up finding that there were some imaginary mode frequencies that came up. We also saw that there were some mode crossings that we had to fix, and thankfully we observed that with the mode characters and moved around our data so that it reflected what we actually found. And as you can see, once we graphed all of them, it gave us a nice kind of linear trend as shown in the figure at the left. And also, once we had all of our frequencies together, we plotted the IR intensity. But we also found that if you shifted the structure a little bit and distorted the atomic positions, you do end up getting Raman intensity, as shown on the figure at the bottom right corner. Some of the main takeaways are that DFT was used in this project to determine the optimized structure that gives better results with tight convergence. And specifically by tight convergence, we use powers of -9 and -8 in the VC relax calculations. The band gaps, band structure, and density of states are in good agreement with other works found in literature, so that confirms that our calculations were correct and we were getting the right results. Also, we found that the structure of cubic cesium lead iodide does not have Raman activity, which we thought it would before due to its stable structure. But we found that with a slight change in the atomic positions, that you do end up having Raman activity. Some future work is to analyze the structural changes due to strain and see if Raman and IR spectra can allow us to see local strain. And hopefully this project can kind of give some insight into increasing the efficiency of solar cells. And thank you everyone for joining my presentation. Lastly, these are the acknowledgements to the Merced cluster, the Stampede 2 cluster, as well as Quantum Espresso for allowing us to run the calculations. And thank you everyone for joining my presentation today. This was my first research project, and I look forward to continue working on it and seeing what else I might find. But thank you for attending.